In this lecture, we're going to introduce the formalism of quantum mechanics. So we're going to be a little bit formal. Okay, and actually we are going to introduce this one in four postulates of quantum mechanics, right? So this gives us some kind of more formal and also more rigorous basis for discussing quantum mechanics. Okay, and the first one is about the state. Okay, but we know that in classical mechanics, what is a state? A state actually is a point in phase space. Right. So of a single particle, of course. And so this is a 6-dimensional. So if you have more than one particle, so you can have say 2 particles, and then you can have a high dimensional phase space. But anyway, a state of a physical system is just a point in the phase space. Okay. And of course, you can also have statistics, right? You can have statistics. So that means sometimes you don't have a certainty, in knowing the states of a classical system. So in this case, we say that you can have a state 1 with probability 1. You can have state 2 with probability 2, right? So on and so forth. Okay. So this is called an ensemble. Okay. So that means you can study the statistics of classical systems. So that means if you repeat the experiments, or if you have many identical classical systems, some of them will be in the state S1, some of them will be in the state S2. And if you have done this experiment many times, or you have many copies of the systems, so you can have different probabilities, right? Okay, so that's the classical mechanics and the classical statistics. Okay, but in quantum mechanics, okay, so it's actually very different. When we say a state is actually a possibility. Okay, so this is one important thing, one very different thing in quantum mechanics. Okay, so in this sense, so classical mechanics actually is talking about is a theory about matter or energy. Okay, right. But quantum mechanics is a theory about information. Okay, so once you have a possibility, that actually you have kinds of information, right? So you said that you have this possibility, you have that possibility. So this is all about the information of the system. Okay, so actually from the shift from classical mechanics to quantum mechanics, if we look with hindsight, actually the key point is is the shift from the matter to information. Okay, so this was probably first noticed by Wheeler in 1970s when he was asked what would be the most important thing in the next stage of physics, and he paused for a while and then answered with a single word: information. Okay. Right. So possibility is actually related to information. Okay. So that's fundamental difference between classical mechanics and quantum mechanics in talking about the state of a system. So this is one thing, right? And we have learned that we can use, say, wave functions to mention a state or a possibility. Right, so you can have, say, percent 1, percent 0, x, percent 1, x, percent 2, x, so on and so forth, right? And we'll also introduce the Dirac rotations. Okay, so you can say 0, 1, 2. So all of this one just, okay, they are just different possibilities. Okay. So this is the rotation of the state. Okay, but in quantum mechanics, we have a very important thing, that's a superposition. Okay, so this is what we cannot have in classical world. So we can have a superposition of different possibilities. Okay, so that means you can have, say, for example, alpha 0 percent 0 x plus alpha 1 percent 1 x plus alpha 2 percent 2 x. Okay, so this gives a superposition. Okay. With this, all of this one, alpha 0, alpha 1, and so on and so forth, they are complex numbers. Okay. Of course, in Dirac rotation, you can also write this one as alpha 0, 0, plus alpha 1, 1, plus alpha 2, 2, and so on and so forth. Right. Okay. So they are superpositions. Okay. Right. So this is the big difference from between classical mechanics and quantum mechanics. So you can have different possibilities, and you can have superposition of different possibilities. Okay, and this alpha I are called the probability amplitude. Okay, of possibility I. Okay, so you can say that. So you can write down this alpha I equals to the probability, square root of probability times the phase factor I, right? Or you can say that this alpha I modulus squared just equals to pi. Okay, and then of course the probability of different possibilities should sum up to be 1, right? Okay, so that's an important thing that we have learned about the states in quantum mechanics. Okay, so you can use a wave function, but you can also use a Dirac rotation. Okay, right. So we can actually have a little bit more. So a few words on the Dirac rotation of states. Say percent, right? So this is a state or a possibility. We use Dirac rotation. Of course, you can say that first of all, it's kind of a shorthand. Okay, so that means it's a very concise. Right, so you don't need to write down. For example, you can have percent n x y z. Not just simply just choose them to be a simple log, right? Okay, so this is one thing that you can save a lot of space. Okay. Secondly, you have a lot of flexibility, right? Since the state is a possibility, you actually can write all kinds of. You can use just a notation to mention this possibility, right? For example, you can use M, of course. You can use MLM. Okay. You can use, for example, spin up. You can say that have a spin going inside, right? You can also use that I have one electron and one positron. Okay. You can also say I have a vacuum and plus one electron and one positron. All right, and also plus one and two photons. Okay. So you have a lot of flexibility, right? So just use your own invention, right? So sometimes you can use say left or right, right? You can create your own symbols just to denote. Okay, it's only to denote a possibility. Okay. Right. So nobody said that you have to use the PHYS or PHYS M or PHYS M X Y Z, right? So you can use any kind of notation that's convenient, that's intuitive, to denote a state. Okay. Right. Okay. So that's one good thing about this Dirac rotation. Okay. But more importantly, I think the most important thing is that so it is universal. Right. That means it does not have to be a real space wave function. Okay. So this is actually important if you want to apply quantum mechanics to different things. Okay. So important for example, you can consider spin. Right. So we say that you can say spin up, spin down, the spin in the x direction, spin in the minus x direction, right? So on and so forth. So actually, there's no way to write down a real space wave function. Okay. Right. And secondly, for example, if you consider vacuum also as a possibility, right? So vacuum is also a state in quantum mechanics, right? Because you can have a system that has no particle, right? So you can easily say that I have a vacuum. There's no real space wave function, right? Okay. So if you want to apply quantum mechanics, for example, to quantum field theory, and then you got of course, a very important state is the vacuum. So the vacuum, you don't have any way to write down the wave function, right? The real space wave function, okay? But we can just use Dirac rotation to say that this is a possibility, okay? So that's an important thing, okay? And the third important application is that many-body physics. Or quantum field theory. For example, if I say that I have one particle with momentum k1 and the two particles with momentum k2, one particle with momentum k3, right, so on and so forth. If you write down this in a wave function, this will be a very high dimension space, okay, right? So a wave function would be extremely complicated. Okay, so that's one thing. And also you can have a superposition. For example, you can have a vacuum plus electron and a positron. You can also have a vacuum plus 2 photons, right? So on and so forth. So in these cases, actually, you can see that you have a mixture of different number of particles, right? You can have 1 photon plus say 2 photons plus 3 photons. Okay. So how to write down this wave function? There's no way to write down this in a wave function. Okay. There's no simple way because this one is in the 3-dimensional space. This one will be in 6-dimensional space, and this one will be in 9-dimensional space, right? So that makes this all of this one to be extremely difficult, right? So the Dirac rotation is not only concise and flexible, but also it is actually essential if we want to study, quantum mechanics in more general situations. Okay, so that's why we want to introduce this Dirac rotations, and then later on, so we're going to use this more and more, and so that you're going to more and more familiar with this important rotation. Okay. Okay. So this is one thing about this Dirac rotation. Okay. All right. So we say that a state is a possibility. Okay. A superposition is possible. Right. So that means you can write down psi as say C1 1 plus C2 2, and so on and so forth. Okay. Okay. So this is two things that I've learned about this quantum state. Okay. And then there's a question. Okay. What possibility? Okay. So at this point, actually, I have been a little bit more advanced. Okay. So we need to discuss this one more in quantum measurement later. Okay. Okay. But in general, a possibility actually is the output of measurement. Okay. For example, M of H hydrogen atom. Okay, so this is a possibility. Okay, with this possibility, the measurement of E is EM, L squared is L times L plus 1, H bar squared. And LC is, if we measure LC, is M H bar, right? So this one define this possibility, okay? Right, so the possibility actually is defined by the outputs of the measurement, okay? So if we have a possible outputs, that means you have this possibility, that means you have this quantum state, okay? So that is the thing that we should keep in mind. So what means the possibility, okay? All right. Okay, so these are the physics, okay? And now let's be a little bit more mathematical. So we call this, we're going to introduce the Hilbert space. Now we know that if a state, if PHYS is a state, and phi is a state, and then the superposition, say alpha PHYS plus beta phi, is also a state for any alpha beta being complex numbers, right? Okay, so this is you know, a factor in quantum mechanics, right? So that's a superposition, okay? So in this sense, you know that then, so that means all states of a quantum object, okay, form a linear space, right? Because any linear combination of them will form this one, okay? So this is one thing, okay? Okay, so this is fact one, okay? And also we say that we can define the inner product. We say that if you have a state, say phi and PHYS, and then the inner product is defined as phi, for example, R complex conjugate, PHYS and R complex conjugate, and phi R, and do the integration, right, in the space. Okay, so this is the definition of this inner product. Okay, and this inner product is also allowed in this one. Okay, and the inner product, of course, have a few properties. Let me write down this properties of this inner product. So the first one is that and this for any two states A and B, okay, the inner product actually is a complex number. Okay. And A and B and B and A, they are complex conjugate. Okay. So obviously you can see that from this one, right? So that's one thing, okay. And secondly, it's bilinear. Okay. So that means if you have say for example A equals to alpha 1 plus beta 2, and B equals to let's say eta 3 plus gamma 4, okay, and this one will give us A and B can be just simply written as the alpha complex conjugate times eta and 1 and 3 plus alpha gamma 1 and 4 plus beta and eta 2 times 3 and plus beta complex conjugate times gamma 2 times 4. Okay, so that means you just do this one, and as if it's a linear combination, right? So just as normal products. Okay. Okay. And another one is we have this so-called Schwarz inequality. Okay. Okay, so basically, if you consider the inner product of two vectors, say if we have M1, N2, okay, so they have angle theta, you know that you must have n1 dot n2. Okay, this one must be less than n1 and n2, right? Okay. So in other words, we say that n1 dot n2, the inner product of this one, modulus squared, should less than n1 dot n1 times m2 dot n2, right? So this is what we have in classical in geometry. Okay. So if we have this inner product to comply to this intuitive picture, so we also say that if we have this A and B, okay. Now this one is a complex number, so we took the modulus and took the square. Okay, take the square. So modulus square of this one, of course, this one should be less than A and A and B. Sorry. Okay. Okay. Right. Okay. And then there's another one, the fourth one. Any two states, any states actually, the inner product between itself is always greater or equal to 0, and the equality takes only when this one is 0. Okay. Right. So these are the properties of this inner product. Okay. So it's actually quite intuitive. Okay. Because of these properties, it's also called this inner product also called overlap. Okay, so let's look at how much this state is kind of overlap with another state, right? Okay, let us do a few examples. Do one example, okay, for you. Like, so let's say the spin up and spin down equal to 0, and the spin up and the spin up. These are just two states equal to 1, and spin down equal to 1. Okay. Let's say, suppose we have kind of y equals to square root of up plus I down. Okay. For example, and the minus y, say defined as square root of so up minus I down. Okay. Okay. So let's calculate, for example, y and y. Okay. And then we use the bilinear property of the inner product. So this will equals to square root of 2. Okay. Right, times 1. And then you have up and down, so that's going to minus I, up and down. And then minus I, down and up. Okay, times square root 2, sorry. And then plus down and down. And you know that this one just 1, this is just 1, and this one is 0, this one is 0, okay? So it's 1 plus 1 divided by square root 2 times square root 2, right? So the answer is just 1, okay? And of course, you can similarly you can calculate the y bar and y bar. That will be equals to square root of 2 and up times square root of 2. Okay. And now this one will be plus I up and down. Sorry, let me think. So this should be plus I. Okay. And so this should be plus I. This should be minus I. Sorry. And up and down. And then plus I down and up. And then plus down and down. Okay. Again, so this one is 1, this one is 1, and this one is 0. Right? This one is 0. Okay. So the answer again is just equals to 1. Okay. Right. So now you can calculate the y and the y bar. Okay. So this will be square root of 2 times square root of 2 in the denominator. Okay. And now up is okay. Okay. And the up and down, so this will be minus I up and down. Okay. And then you have minus I down and up. But now you have another term is minus down and down, because if you look at the y, it has I right here. I bar is minus I here. So I times minus I is 1, right? But you need to take its complex conjugate. So if you look at this bilinear equation, you have to take the complex conjugate of the coefficients in the first step. Okay. Right. So that gives you a minus I. So minus I times minus is just minus 1. Okay. So then this one and this one 0. But this one is 1. This one is also 1. 1 minus 1 is 1. Is 0. So this one is 0. And similarly, and remember, we have another property, right? It's just a complex conjugate, right? So this one should also be 0. Okay. So you can see that in this sense, and this y and y actually, have very similar properties as this up and down. Okay. So in up and down, both of them are normalized. So they have inner product with themselves is just 1, and the mutual inner product is just 0. Okay. And then you can have the same facts phenomena for the y and the y bar. Okay. Right. So they also are normalized, and they are also mutually have a 0 inner product. Okay. Okay. So that's one example. Okay. And then the third one thing we want to mention that so if percent and phi equals 0, we say that percent and phi are orthogonal. Okay, this is math. So in physics, we say that the two possibilities are mutually exclusive. This is physics. Okay. We're going to have more on this one in quantum measurement theory, but let me just give you one example. Okay. Okay. So more in quantum measurement. Okay. But now we say an example. Let's consider M, say M1 of hydrogen atom, okay, and M2 of hydrogen atom. Of course, we know that M1 and M2 are equal to 0. So they are orthogonal if M1 does not equal to M2, right? Okay. So this is the math. Okay, so that's math. But physics. So what means M1? Okay. So M1 actually is the eigenvalue of LC, right? So that means so if LC has 100% probability in M1 H bar, okay, and then has 0% probability in M2 H bar, and vice versa, right? So that means if you have LZ has 100% probability to be M2 times H bar, and then you have 0 probability to have M1 H bar. Okay, so that means these two are actually mutually exclusive. Okay, right. So if you have two orthogonal states, so that means you have two possibilities, which are mutually exclusive. You cannot, if you have a certain certainty in this possibility, and you would have no possibility, no probability in another possibility. Okay. So this is important about this orthogonal states. Okay. And another state is that if you have a PHYS, and this one is the same as PHYS for any complex number which is not 0. Okay. So that means so if we have this one is PHYS, if you want to use a vector to denote this one, and say that you have another one, okay, this is C times PHYS. It's the same physical possibility. Okay, so that's an important thing about this, notation of the vector of this one. Okay. All right. So with all of this one, now we can just summarize. So just write down as a summary. This actually is a postulate 1 of quantum mechanics. That is a state is a ray of vector in a Hilbert space. Okay. So what is a Hilbert space? A Hilbert space is a linear space. It's a complex. Okay. So it's linear space with complex coefficient and with inner product. Okay. And the second thing is that PHYS is called a vector in the Hilbert space. Okay. And this one and this one actually correspond to the same. Physical, okay, mathematically they're different. The same physical state. Okay. So Hilbert space actually it's a linear, it's a very simple linear space with complex coefficient and inner product. But the physical states, they are just a vector in the Hilbert space. They is not exactly the Hilbert space actually. This there are also a lot of misconceptions in quantum mechanics. So this is one of them. People always say that a physical state is just a state, a vector in the Hilbert space. Actually, it's not. It's a ray. Okay. So that means it's a ray. Okay. And thirdly, 0 is not a state. Okay? So it's like a, right, if you say consider a hyperspace like this one, let me use different color. Right, so if I have a space like this one, okay, so now you can see that first of all, so this one should be removed. So this one should be removed, okay, and then all of this one and this one, they're the same state, and this one and this one are the same state, and this one and this one are the same state, okay, and this one and this one are the same state, okay, and this one and this one are the same state. So you can see that if we make all of this one, so the physical state, actually you can say that is something like this one. First of all, it's like a sphere, okay. It's not like a usually a two-dimensional space, because all of this one should be combined just into one point, okay. So this one actually stands for array, okay. And secondly, not only like this one, actually this one and this one are equivalent, okay. So you can say that this one and this one are equivalent. You can say this is A and then this is A. They're the same. And this is B. This is also B. Okay. So it's only half of this. And the other half actually is just equivalent. So it's a sphere. So all of this together make it a physical state space is a highly non-trivial curved space. Okay. So don't think that the states, quantum states, are just very simple. They are just like vectors in a, in this kind of plane space. No, it's not. The physical states, because of this equivalence, so actually form a very non-trivial curved space. Okay, later on we're going to see that for the spin half, right? The very simple space, the two-dimensional Hilbert space, actually is corresponding to a sphere. Okay, and if we go to high dimensional, more states actually is very non-trivial. Okay. Well, okay, right. So this is the postulate one. Okay, it's an array. Okay, of vector in the Hilbert space. It's not just a single vector. It's an array of vectors. Okay, right. Okay. So if we have a linear space with an inner product, okay, right? This is a Hilbert space, right? So we can choose a set of vectors, say 1, 2, 3, okay, such that, okay, m and m prime equals to delta m prime. So that means if they're the same, it's normalized. If they're different, they're orthogonal. Okay, so these are called orthonormal, right? Okay. And you know that if we have a space, the number of such states is bounded to be, say, a certain number, m, okay? And all of them are linearly independent. Okay, so that means you cannot write 1. Okay, so that means you cannot write, say, m equals to summation of I, c, I, and m. Sorry, I for I does not equal to m. Okay, this is not possible. Okay, there's no way to write any of this state into a linear combination of others. Okay, right, and since this is this one, so we call this Hilbert space is n-dimensional. Okay, and then upon that, all states satisfy the same physical conditions. This is important. Okay. That can be expanded. Okay. Okay. This is called expansion, and it's unique. Okay. Actually, it's very easy to find out what is Cm. The Cn can be written as m and the %. This is very easy to prove. But this is m summation of I equal to 1 and to m, ci and I, right? That equals to a summation of I equal to 1 to m and I, ci, right? Because it's linear, okay? And this one is a delta function, so that equals to Cm, right? Okay. So with this condition, so this one is called a complete list, okay, of this set. Okay. So that means if we have n-dimensional Hilbert space, we can always find the m basis states. Okay, they are also normal, and they are complete. Okay, so this one is called a orthonormal complete basis. Okay. Right. So let's take a break, and then we're going to have a little bit more specific, more concrete discussions about this expansion. Okay. All right. So see if you have questions. Okay, please just write down in the chatting room. Okay. Right. So since if I have n-dimensional Hilbert space, so you can choose, for example, 1, 2, m orthonormal complete basis, right? So that any psi can be written as a summation of m equals to 1 to capital M, Cm, and m, right? So this is always possible, and with the coefficient equals to m and the psi, okay? And this m actually can be infinite, okay, as we have discussed in the previous question. For example, if you consider the 1D harmonic oscillator, right? Okay. Right. So if we wanted to be more, if you are not yet very familiar with this Dirac rotation, let me just write this one again. Okay. In terms of wave functions. Okay. Right. You can have, for example, psi m and x. Right. Okay. So that form the computer basis with this orthonormal condition, and any psi x can be written as summation of m Cm psi m x with Cn equals to psi n complex x. Right. So this is what we have in terms of the wave functions. Okay. Right. Okay. Let me give example. Okay. For example, right, you can consider states 4, 3, m. Okay. For m equal to -3, -2, -1, 0, +1, +2, +3. Okay. Right. So this form the basis of a 7-dimensional Hilbert space. Okay. And obviously you can have 4, 3, m and 4, 3, m prime equals to delta m, m prime. Okay. Okay. So these are the, and any states, any 100 atom states with the physical condition. Remember the same physical condition. E equals to E4, that's minus readable energy divided by 4 squared. And L squared equals to 3 times 4 times h bar squared. Okay, with this one, suppose we have any state psi satisfy this condition. Remember, must satisfy the same physical conditions, can be expanded by summation of m, Cm, 4, 3, m. Okay, and this Cm can be determined by just 4, 3, m and psi. Okay. Or in real space wave functions, you can say that can be written as a summation of m, Cm, okay, psi, 4, 3, m, r, theta, phi, right? Remember this one will equals to summation of m, Cm, r, m, 4, 3, r, theta, 3, m, theta, and phi, m, phi, right? Okay. So any states satisfy the same physical conditions can be expanded. Okay. So that is the orthonormal basis. Okay. So you don't have to say this physical condition is the boundary condition. It could be. So the physical condition actually means so per se satisfying the same physical conditions of the basis. Okay. Can be expanded uniquely. And so this must be emphasized. This includes, first of all, boundary conditions. And secondly, for example, can be energy by L squared or LC actually, or momentum, whatever, okay? You can just choose any physical condition to constrain the set of states, okay? Sometimes you can say just have the same energy. Sometimes you can say they have the same energy and the same total angular momentum, okay? But you must have then to satisfy the same physical conditions so that they can expand it. If they don't satisfy the physical conditions, it cannot, right? For example, the state 5, 2, minus 1 r theta phi cannot be expanded by 4, 3m. Okay, they're actually orthogonal. Okay, to all of them. Okay, so because they don't have the same physical condition, because they have different physical conditions. The energy is different, and the angular momentum is different. Okay, so this is one thing I wish to emphasize. Okay, so when we say that it's complete within a certain condition. Okay. Okay. Of course, this is always true, right? So you must consider the same physical system, right? So you must, otherwise, you're talking about a different physical system. How can you expand the state of one physical system to the state of another physical system, right? So that's one important thing. Okay. All right. With all of this, now we can say that we can introduce this matrix representation of a state. Right. So remember, all this per se can be written as C1 and 1 plus C2, 2 plus and CM, right? Okay. So then, suppose with 1, 2, m given. Okay. If this is already given, and per se actually is uniquely determined by C1, C2, Cm, these coefficients, right? So that means if you know the coefficient, then you know the state, or if you know the state, you know the coefficients. Okay. So knowing any of this one, so we can say that so we use a column matrix. Okay. So this is of course it's m times 1 a column matrix. Okay. Represent the state. Is that right? Okay. So this one is called the the matrix representation. Okay. All right. And then actually you can, if you want, you can say that then the PHYS, state PHYS can be actually written as PHYS, sorry, 1, 2, 3, and M, and times C1, C2, Cm. Okay, so this one is 1 times M matrix, right? This is N times 1 matrix. So this will give you 1 times 1 matrix. That's C1 and 1 plus C2 and 2. Right, just for fun. Okay. Okay. And now you can also define the Hermitian conjugate of a matrix. Right? We know that if we have a matrix A, and the Hermitian conjugate is defined as you take the transpose and then do the complex conjugate. Or if you look at the, for example, you have this A11, A12, or the A21, A22, right? Okay. You take the Hermitian conjugate, you do the transpose. So A11 is still A11, A22 is still A22, okay? But A12, this one will be A, become A21, A12, okay? And this will be A21, okay? You can say that they actually exchange. Okay, you do the transpose. Okay, so this is for the transpose. Okay, so let me use the color, red color for transpose. So this is transpose, make this 1, 2 to be 2, 1, and 2, 1 to be 1, 2. Okay, and let me use the green color for this complex conjugate. So you take the complex conjugate. Okay, so basically we said that so the complex conjugate of the matrix elements will equals to, so you exchange the indices and then take complex conjugate, right? So this one is the transpose. When you do a transpose, you can change these two indices, okay? And then furthermore, you do the complex conjugate, right? Like this. So that's the definition of Hermitian conjugate of the matrix. And then of course, for the state, right? For the state, we can also define the complex conjugate. So this will equals to C1 complex conjugate, C2 complex conjugate, and Cm complex conjugate. Okay, so right, so this of course equals to PHYS T, do the transpose, and then takes complex conjugate, right? So this one of course is 1 times M. It's a raw matrix. Okay, right? So that is another state. And now you can say that, so if you look at the inner product, okay, suppose we have PHYS equals to C1 and 1 plus C2 and 2, Cm and M. I have another side phi equals to say D1 and 1 plus D2 and 2, and so on and so forth, plus Dm and M, right? Okay. And the inner product is of course say PHYS and phi, that equals to, okay, C1 complex conjugate times D1 plus C2 complex conjugate and D2 plus Cm complex conjugate and Dm, okay? And this one actually can be written as a matrix form. There's C1 complex conjugate and C2 complex conjugate and Cn complex conjugate and times D1, D2, and Dm, okay? So this one is 1 times M matrix, and this one is M times 1 matrix. So all of this one together will give us 1 times 1 matrix, right? So that is C1 complex conjugate C1 D1 plus C2 complex conjugate D2, and then plus Cm complex conjugate Dm, right? Okay, so this one in the matrix form is just Hermitian conjugate of this matrix per side and times phi. Okay, so with this, we can say that you can transfer the per side into a matrix. This is n times 1, a column matrix. Okay, and now we can say that this one changes to be per side deck. That is 1 times m, a row matrix. The inner product per side and the phi will change to be, okay, so it's 1 times m times 1. Let's give us a 1 times m, well, sorry, 1 times 1 matrix. Okay, so 1 times 1 matrix is just a C number, or the complex number. Okay, right. Sometimes we also say that we call this say Cj that equals to, sorry, Cm that equals to m and per side that equals to, we call this one per side m. Okay, sometimes we call this per side m equals to Cm equals to m per side. We call this one wave function. Okay. Okay. Right. I like this one. Just leave this message to you. Okay. Okay. It is a hint for you to think. Okay. But I will not talk too much about this. Sometimes we call this one wave function. Okay. But anyway, so this is the matrix representation of a state, a matrix representation of the inner product, right? A state. Okay. So we call this state a cat state, and call this one a bra state. Okay. And call this one a bra Kate. Okay. A bracket is a C number, and this one we call this as Q numbers. Okay. Right. So that is the state. Okay. So much about the states. All right. So that's postulate 1. We have introduced the states. We introduced the direct rotations, and also we say that if we have a basis, okay, and this is we're going to have a matrix representation. Okay, so the final word about this matrix. So there's one remark. Okay, on the matrix representation. So it depends on the choice of the basis. Okay. Like for example, if we have a state, say per side equals to, say for example, 1 plus 2, like this one. And if we choose to say 1 tiered equals to 1, and 2 tiered equals to 2 times I, imaginary number. And then you find that this per side, of course, that equals to square root of 1 tiered minus I, 2 tiered, right? So the matrix will becomes 1 minus I. But in this case, percent, the matrix is 1, 1. So you can see that let me call this the percent here. So you can see that the matrix presentation, actually representation, depends on the choice of the basis states. Okay, if you choose different basis states, you got different matrices. Okay, so that's one thing for you to keep in mind. Okay, so I'm not going to discuss too much into this mathematics. Okay, right? Of course, then for more, so we can discuss this one in another quantum mechanics course, quantum mechanics 2. Okay, but we have know the essential things about the state vectors in the Hilbert space. Okay, and then now we come to the postulate 2. Okay, so this basically says that a physical quantity is an emission operator in the Hilbert space. Okay, let me explain. Okay, so there are a few things that we need to define. Okay, first of all, what means operator, and more specifically, what means a linear operator? Okay, in the Hilbert space. Okay, so basically, an operator changes state into another state. Okay, so this is an operator. So that changes state to a new one. Okay, but this could be anything, right? But what we are more interested in is that it's linear. If it's linear, that means if you have two states alpha per psi plus beta phi, for example, you have two states, a linear combination. Okay, so this one actually can be written as they separately and then do the summation. And then these coefficients can be moved outside. That means it's linear. So equals to alpha equals to alpha per psi prime plus beta phi prime. Okay, so this is this means linear. Okay. Okay, so we're going to discuss this kind of linear operators. All right. Since it's linear, that means so if we know how this operator acts on the basis states, right? Say OM change to be M prime. Okay, and then we know how this one acts on any state per psi, right? Because per psi can be written as a summation, right? So we can apply this one. So O acting on per psi actually can be written as O. The summation is C1 and 1 plus C2 and 2 plus Cm and M, right? Because it's linear, so this can be simply written as C1 and transfer the 1 plus C2 and transfer 2 and Cm and M prime, right? So as long as you know what's this, and then you know the transformation of any states, okay? So that is a very nice thing about this linear. Okay, so all of this linear will give us this simplicity of the actions on the states. Okay, so you don't need to know the transformation on all the states. Just node state transformation on the space states will be sufficient. Okay. Okay. And then in this case, remember this M prime is also a state in the Hilbert space. So we also expand it. Okay. So let's expand this one as say, for example, let's say call this one A, B, C, D. Let's call this one alpha M and M. Of course, this is possible, right? And then this alpha N, of course, is very simple. It's just M, the inner product between M and M prime. And that's, of course, it's just M and O M, right? Sorry, let me call this one M. Okay, because I don't want to repeat to confuse this. Okay, is that this one? So this is nothing but just a matrix element, right? Okay. So you can say that now you can say that O acting on this state will just equal to the summation of O M M and M do a summation of M equal to 1 to M. Okay. All right. So this one, sorry, with OMM, just you act in a state on the state M. Oh, sorry, I made a mistake. So this should be OMM, okay. Right. Sorry. Okay, like this one. Right. So now you can say that if you have you call this one a matrix, okay, and this new state will be just if you act on this one on the state per side, okay. So that will be simply just equal to summation of M equal to 1 to M, Cm, and O acting on this M, right? So this just simply equals to summation of N equal to 1 and M, Cm, O, M, M, and M. Okay? Okay? So now you can call this one per side prime, that equals to O per side. Okay? That equals to, say, C per side prime M, do a summation of M, right? Of course, right? And now this one equals to the summation of N equal to 1 and M, say, sorry, this is, there's a mistake right here, it's M, M, okay. O, M, M, C, M, and then do the summation of M, oh, sorry. M, right? Okay. So you can see that this one will just equal to this one, right? Because this is dummy, so you can just call this one M, right? Okay. So that means Cm prime just equal to summation of M, O, M, M, Cm. So this is the coefficients for the new states. This is the coefficient of the older states. And this one is so much like a matrix products. It's M to 1 and to 1, right? So if you write this one as a matrix, this is psi prime. So that equals to matrix times the older one. And this matrix has matrix elements. So this one is n times m. And remember, this one is m times 1. Okay, so this one must be m times 1, right? Okay, so with this one, so any operator become a matrix. It's m times m matrix with elements mm just equal to m. So you acting this operator on the basis state m, you got a new state, and check how much this one is overlapped with the original basis states. So that define the matrix elements of this one. So this way, you have the matrix representation of okay, of the operator, right? Of a linear operator, okay? So because you just know how this one acts in a state m, so that can equal to summation of m o m m and m, okay? Right? With this o m m, of course, just equal to m, the overlap between this m, right? Because this one can be also expanded using the order basis, okay? Right, so this O matrix is m times m matrix, okay? And then the state per psi, we just change to be something like this one, right? So the operation becomes a matrix product. Okay? Right, so this gives us the matrix representation of the operators, right? So if you still remember, right, recall Lx, right, acting on the states, say 2, 1, m, right? Remember this one has a matrix h bar over square root of 2, and this is 0, 0, 0, and this is square root of I think it's, sorry, this is 2. Over 2, square root of 2, and square root of 2, square root of 2, square root of 2, and 0, 0, right? So that one, so this got a new state, and this state can be expanded into the basis of the original one, right? So you can find that if you have this one, for example, you act in this one on the 2, 1, minus 1, plus 1, okay? So just apply this one. So that equals to h bar over 2 times square root of 2, let's say and 2, 1, 0, right? So that's the and so on and so forth. Okay, so you can do this one for the other states. So that's what we have done in the exercise, right? So if you still remember this one, so that's a way to. So if you know how to transfer the basic states, and then you know how to transfer general states, right? Using this matrix form. Okay. Right. And also you can apply this one to 2. For example, if you have 2 operators, say if you have a combination of two operators, for example. So you can have B acting on M. You can have A acting on M, right? Like this one. So this is actually defined as A, B acting on M, okay? Right? So then again, you can see that you can take the matrix elements of this one. Okay, so let's calculate this one. Look at what it is. So this one actually equals to right. But remember, so that one simply just equals to M A summation of say K and B K M and then K, right? So that's so then this one equals to summation of K B K M and M A and K, right? And this is just a matrix element of A M K, so B K M, right? So this just uses the matrix times B and takes M and M, right? So you can see that. So if you have, suppose you have, so if AB equals to operator C, and then the matrix A and the matrix B actually also equals to the matrix of C, okay? Right, so just follow the same algebra for matrix products, okay? So you can, okay? So the matrix algebra just is the same as the algebra for the operators, okay? Right, so this is a very nice thing. So that means if you know everything about these matrices, and then you actually can just do the same thing for the operators, okay? So this make all the operations will be very convenient, okay? Right? Okay, and now let's consider a special let's say a matrix. Okay. Right. So remember, we have if you have a state, you can have C1, C2, Cm, right? You can have the image conjugate. That's a D1 complex conjugate, D2 complex conjugate, and Dn complex conjugate. Okay. So this one is n times 1. This is 1 times m. So if we do the matrix product per psi and phi deck, okay, so this will become a matrix that is n times m, right? Okay. So be very careful. This one is not this one, okay? So this actually is phi and per psi is 1 times 1, okay? This one is m times m, okay? They are different, okay? So the order of the matrix, this is one is n times 1 matrix, another is 1 times n matrix, okay? So if we change the order, they actually got totally different things, okay? But then what is this one? So this will be, if we just do this elementary matrix product, this will be C1 times D1 complex conjugate. And C1, sorry, let's say C2 times D1 complex conjugate, and so on and so forth. This is too small space. Let me erase this one and rewrite this. Okay. So this will be C1 D1 complex conjugate, C1 D2 complex conjugate, and so on and so forth. This will be C2 D1 complex conjugate. Okay, this will be C2 D2. Okay, so it's a m times m matrix. Okay, and this matrix actually is quite interesting. right? So if you want to transfer this into an operator, this one will equal to what? Okay. Right. Let's define this a new operator. Say M, just define as a matrix. Define as a percent and a phi deck. Okay. So the question is, what is the operator of this? So let's check this one. Let's apply this one to kind of vector. Okay. See what will happen. So this will equals to percent and phi deck and eta, right? So eta is also a matrix. So this is m times m. This is m times 1. Okay. So this is 1 n times 1. This is 1 times m. This is n times 1. But remember, when you do the matrix, you can do this way, right? You can do the products like this first. But what is this one? This is just inner product of the states, right? So this just equals percent phi deck. Sorry, phi and eta. Okay. Right. So that means if you act in the operator on the state eta, it will just becomes the state percent and the phi act on eta. Okay. So this gives us a very nice thing. So we say just call this m just equals to percent and eta. Okay. So that's a very strange thing. Okay. So this way is not. Okay. Of course, this is just a C number. This one is an operator. So what does this mean? So if you look at this data, actually, so what does M acting? So M acting on percent actually equals to, sorry, on the state, right, equals to percent and eta and, sorry, phi and eta. So this one actually is you first calculate the overlap. And then this is the final state. Okay. So that means for any input state, it always output the same state. Okay. But with the coefficient, given by this overlap. All right. So this is so this one we call this this is the Dirac notation of an operator. Okay. Right. And you can, more interestingly, you can even define the state, for example, if m equals to m and m. Okay. This is the basis state. Okay. So then you can see that the matrix element, the K, M, L. This is the matrix element, KL. So that of course equals to K, M, M, L, right? So just equals to delta Km, delta ML. So what does this mean? That means this matrix will just equals to 0, 0. They're all 0. But there's one term that is 1. Okay. And this one is the case row, and this one is the else column. Okay. right? So if you have such kind of a matrix, and then you can have a term like this one. But you can, of course, you can also say that what if I have an operator like this one? Say m times m. You do a summation of this one. And then this matrix will just simply just m11, m12, okay, m21, m22, okay. Right. So that means any operator all can be written as summation of mm, o, mm, and m and m, okay, with all the matrix element just equal to m, o, and m, okay. So this is the rack rotation. Okay. So that gives us a set of operations and notations, okay. Right, so now you can summarize this kind of rotations, the Dirac rotations. Okay, so you can have a state per se, and the Dirac rotation is per se, and the matrix is C1, C2, like this one. So this one is the n times 1 matrix. You can have per se compass conjugate, and they have the Dirac rotation is this one, okay, and this is C1 compass conjugate, C2 compass conjugate. This is 1 times n matrix, okay. You can have the inner product, okay, and that is just per se and phi, okay, and this will be just C1, C2, and times D1, D2. This is 1 times m. This is n times 1. So altogether give us a C number, right? That is 1 times 1. But you can also have something that's very strange. You don't have any corresponding like this one. So it's phi and this one. And now this is going to be D1, D2. Now it's a C1 compass conjugate, C2 compass conjugate. So this gives us m times m matrix. Okay. So this is the operator. Okay. Right. And of course, you can also have a complex number. Okay. And this is a complex number. This is a 1 times 1 matrix. Okay. Right. So this one is a complex number. This one is a this one is a complex number, and others actually are not the complex numbers. Okay. So they are called a cat state. This is called a cat. This is called a bra state. This is a C number. This is an operator, and this is a C number. Okay. Right. So that is all the notations that you can have, in quantum mechanics. Okay. And then you need to, if you write a sentence in quantum mechanics, you need to make sure it's legible products of matrices, okay? Right. So you need to make all these kind of products to be correct in quantum mechanics. Right. So you can have, for example, product. Okay. Let's say, for example, you can write something like this one, per psi and a phi, eta, okay, and a C number, and then you have say chi, for example, and then you have something else. Okay, let's check this one. This one is if we translate into matrix, this is n times this is 1 times m, this is n times 1, this is 1 times m, this is 1 times 1, this is 1 times n times, let's say. Okay, this is n times 1. Okay, this is let me use the operator. Okay, so this is n times m. Okay, So far, so good, right? So this one is 1 times m, n times 1, 1 times m, n times m, n times 1. So this is a good product. Okay. So the result is going to be will give us a 1 times 1 matrix. That is just a C number, right? A complex number. Okay. Well, let me give you another example. So let's have an operator acting on this one, and plus eta, and then phi. Okay, let's check this one. So this is m times m. This is 1 times m. This is n times 1, and this one is sorry, n times 1, 1 times m. Okay, from this one, this combined is okay, and from this one is okay. Okay, but no, this is n times m. This is 1 times 1. So that means this one is not correct. Okay, it's an incorrect formula. Right. Let's give another example. Okay. For example, if we write down psi, c, and phi, okay, like this one. This one is 1 times m. This one is 1 times 1, right? And this one is n times 1. And looks like you cannot have this, right? So look like this one is it's not correct. But however, remember, we can say that if we have c times phi, you can also say that this one is c times, you can take this as identity matrix. So c can be taken as c, 0, 0. It's n times m, okay, a unit matrix times c, right? So this one can be also understood as n times m, okay? So that means the final result is that 1 times 1, n times m, and n times 1. So all of this one together give you a matrix 1 times 1, okay? It's a C number. Okay. So in quantum mechanics, you must have, if you use the Dirac rotations, you write an expression. So this expression, you can always take this as a matrix products, okay? And then do everything as, as if they are matrices, okay? And to check whether this is a correct, or at least it's a legible formula, okay? So that is just called the syntax of Dirac rotations, okay? Right. So we have a state, a cast state, a broad state, the inner product, the complex coefficients, and also we have operator, okay? Right. So that's the Dirac rotations of all of these things, okay? All right. I think we have enough introduction of this Dirac rotations. So you need to do probably some exercise to get more familiar with these rotations. Okay. So in the next lectures we're going to introduce more. Okay. We also try to go back and forth between the Dirac rotations and the wave function rotations. Okay. But eventually, when we talk about spin, we will move fully to the Dirac rotations. Okay. So you need to eventually get more familiar with with these notations. All right. So it's not difficult, just kind of a language. Okay. So you need to understand this syntax. So let me stop right here and see if you have questions.